Peut-être Abdou, on peut démarrer comme ça, on fait l'introduction. Okay, so hello everyone. So welcome to this doctoral course given by Mathieu Laurière and organized by University Mohammed VI and the University Sadi Ayad from Marrakech. This is also organized by Université Côte d'Azur and Laboratoire Euro-Maghrébin in mathematics from CNRS. So for these lectures, we have the great pleasure to listen to Mathieu Laurière. So Mathieu now is Associate Professor of Mathematics and Data Science at NYU Shanghai, and he's also a visiting faculty at Google Research. Mathieu did his PhD at Université Paris 7 a few years ago, and then he was a postdoctoral fellow at NYU Shanghai and also postdoctoral research associate at Princeton University. And Mathieu has become a worldwide known expert in mean-field control and mean-field games, and especially numerical methods and learning methods for these types of models. And so we have the great pleasure to have him for 6 lectures. So today, Introduction to Images. This afternoon, Classical Numerical Methods for Images. Tomorrow, same schedule. So the schedule is 9 a.m. noon UTC +1. So for those of you who are, for instance, in France, this is 10 a.m. to 1 p.m. And the same schedule in the afternoon. So 1:30 a.m., 1:30 p.m., 3:30 p.m. UTC +1, and the same for Friday. So 6 lectures. So this is on Zoom, and this is also on YouTube. So Mathieu is going to share his slides. If you have any question, maybe the best is that you put them on the chat. And so you can, this will be, I'm going to manage the questions. So certainly you won't be able to ask your questions directly online. So once again, you have to put them on the chat. And depending on the way the course is going on, either we can transmit your question online or in live, or only at the end of the class. But in any case, you can put your questions on the chat, and we will share them with the speaker. So Mathieu, once again, this is a great pleasure for us, and thank you a lot for these lectures.
Well, thank you very much, François, for the introduction. And I would like to thank a lot the organizers for inviting me to give these lectures and for organizing everything. And so, yes, it's a great pleasure to give these lectures on numerical methods for mean-field games. And I will start today with an introduction. So let me start with just a few words about the course. So as François said, there will be 6 lectures, 15 hours in total, over the next 3 days, 3 hours in the morning, 2 hours in the afternoon. The main objectives, from my point of view, are 1, to introduce mean-field games. So I know that François gave similar lectures a few years ago, but I don't assume that everyone attended these lectures. And I saw that there are maybe 300 people who signed up for this course. So I don't assume everyone knows mean-field games, and I didn't want to miss the chance to present mean-field games. So I will spend quite a bit of time doing that and introducing ideas that I will reuse again and again later in the lectures. So for today, there will be very little, this morning at least, there will be little numerical methods, but I will present ideas that will be used later on. Second point, so presenting main ideas behind several numerical methods, let's say at the abstract level, but I also wanted to present codes. So I cannot provide code for absolutely everything I'm going to talk about, but I will try to provide samples of codes for illustration and for pedagogical purposes. So I'm not claiming that these codes are optimal or that they should be used for industrial applications, not at all. This is just for illustration, but I hope you can play with these codes and it will help to make things more concrete. One disclaimer, this is an interdisciplinary topic, meaning that I'm going to use tools from game theory, stochastic analysis, partial differential equations, numerical analysis, machine learning. So probably not everyone is interested in everything, but I think presenting a global overview can be helpful. And definitely these different aspects are interacting. So I hope you will find interesting material depending on what you are working on. Feel free to ask questions, as Francois said, through the chat or later on by email if you want. The slides are available on my webpage. So if you go to this address, I have already uploaded the first 3 set of slides. So for this morning, this afternoon, and tomorrow morning, I will probably update a little bit the slides before tomorrow morning, but you can take a look. And I want to mention that what I'm going to present is not just my work. It's based on the work of many people in the community, many contributors, in particular, many collaborators. Of course, the first one was my PhD advisor, Eva Jdu, who worked a lot on numerical methods. But I want to thank all my collaborators because I learned a lot from these interactions. All right, so I will start with some motivations. Many agent systems are somehow present in many situations, either in nature, let's say animals, other than human beings, human societies, and also in distributed AI systems that we create these days. These are quite visual examples, but there are also less visual examples. For example, in economics, maybe when you go to the supermarket, somehow you interact with other customers through the price. So it's not a very direct interaction, but nevertheless, it is an interaction with many agents. Same thing for financial markets. Energy production, so the way we produce and consume energy also involves a lot of agents. This could be important, for example, to reduce carbon emissions, at least the emissions due to energy production. Telecommunications, so you interact through bandwidth and signal, etc., with other agents, and more generally, networks. So if we take a look at groups of animals, for example, flocks of birds or fish or herds of other animals. These have been extensively studied from the mathematical point of view, including some predator-prey models, for example. So maybe you are familiar with the Lotka-Volterra system, which is a system in continuous time and describes the evolution of population of animals, or at least it is interpreted in this way. And similar systems have been studied a lot from the mathematical point of view. They are not trivial. There are many things you can do about these systems. All right, we have systems to describe groups of animals. Very often, these systems are completely determined up to the choice of a few parameters. Now, when we go to groups of human beings, maybe the situation is a bit more challenging because human beings are rational, so they take decisions trying to anticipate what other people do. Maybe animals do the same, but at least for human beings, we are pretty convinced that that we are rational. And so one question is, how can we integrate that in these dynamical systems? Maybe it's not enough to have a dynamical system completely fixed. Maybe we want to have this component of rationality. So here is one slide about a few things that that are not mean-field games somehow. So in case you are familiar with these concepts, I just want to clarify, but probably it will be clearer later on when I actually talk about mean-field games. But just at the beginning, I want to try to avoid ambiguities. Maybe we can revisit these slides at the end. So it's not a pure dynamical system, because in dynamical systems, there is no rationality, typically, no optimization. Agent-based models are typically micro scale. So you try to model the agents one by one somehow and do some simulations. And the agents are typically boundedly rational. So in mean-field games, we are going to look at the macroscopic point of view. And we are going to assume that the agents are perfectly rational which may or may not be true, but it's an assumption we are going to make, at least for most of the literature. Game theory, so this is very connected to mean field games. However, typically it is focused on games with a finite and usually small number of agents. Evolutionary game theory is dynamic, but typically there is not a complete rationality, and the agents are mostly updating their strategy step by step. So step after step, the agent updates their strategy in a kind of almost myopic way until maybe they converge to something or maybe not. So it's more related to the question of learning equilibria, maybe. But in mean field games, the basic setup of mean field games, we're going to assume that the agents solve the game perfectly, and it's not about iterative updates somehow. And non-atomic anonymous games are very used in economics in particular. This is very related because you have an infinite number of agents that are rational. However, one key difference, and probably this will be clearer when I introduce mean field games, is that each player has her own index. So you try to model all the agents, really a continuum of agents, whereas in mean field games, we are going to focus on one representative agent, and this representative agent will be enough to understand the behavior of everyone somehow. So this is a simplification that will really enable numerical methods to work efficiently. So one slide about what mean field games are, from my point of view, at least, and how they can be used. So if you start from an n-player game, which is really what we have in practice, we have games with finite number of players. So n-player game means a game with n players. You let the number of players go to infinity, and under some assumptions, you obtain a mean field game. From this mean field game, we can phrase optimality conditions or equilibrium conditions to characterize the equilibrium, typically using forward-backward systems. And then this is what we try to solve using numerical methods. We obtain the solution to the mean field game. And the important motivation is that if you go back to the n-player game, you obtain an approximate equilibrium. So maybe it's not a true Nash equilibrium, but it is an approximate solution. And for practical purposes, maybe this is enough. So what I'm going to do today, actually, is to cover, at least for this morning, I am going to cover everything besides numerical method. So actually, I'm going to start from n-player game, discuss how to pass to the limit, how to phrase the mean field game, how to characterize the equilibrium. And I will also give an example of why it is an approximate equilibrium for the n-player game. And then after that, starting from this afternoon, we can focus on really numerical methods. But I thought it's important to present the other aspects so that you really understand the motivations and also the ideas behind numerical methods. So for this morning, lecture 1, I will start with the static setting. So here I am taking not one step back, but maybe many steps back from mean field games, starting a little bit far away, but just because it is simpler to explain things in the static settings. Then I will go to the dynamic setting and explain optimality conditions. That will be the basis for numerical methods that will follow up in the next lectures. Lecture 2, 3 about classical numerical method, I put that between quotes because it's just to say that this is based on numerical analysis that has been developed throughout the 20th century and beginning of the 21st century. And lecture 4, 5 will be about deep learning, which is more related to recent developments of machine learning. And similarly for lecture 6, reinforcement learning. Some references, I couldn't put everything, but I tried to put some references in case you want to learn about mean field games. So there are several references introducing mean field games, like surveys or lectures. In particular, the lectures of Pierre Guillon at Collège de France, many of them are in English. Lecture notes of Pierre Cardaliaguet. And I want to stress this volume of the AMS Society, edited by François, which was based on lectures given for the AMS short course in 2020. And in this volume, you can find in particular this reference. So I contributed to a survey on numerical methods for mean-field games and mean-field type control. And many of the plots and many of the examples that I'm going to give are, you can find them in these lecture notes. So if you want a written version of what I'm going to say, a lot of things, not everything, will be in this survey. There are also monographs. So in particular, the book of Bensoussan, Fraisé, and Yam, and the 2-volume book of François Delarue and René Carmona, which contain a lot of information, particularly about the probabilistic point of view, but not only. All right, so let me move on to now mean-field games in the static setting. I don't know if there are already questions, maybe not, but in any case, feel free to ask questions in the chat, and I can take them maybe during the lecture or maybe at the end or before the break or before the other break. So I will start with a static setting, start with finite population game before moving on to mean-field games and describing briefly the notion of social optimum, which will be related to mean-field control. Maybe one thing I can say is these slides probably contain a lot of information, at least if you are not familiar with mean-field games. But feel free to take another look later on. It's okay. You don't need to understand absolutely everything I'm going to say. So you can take another look later on to the slides and understand the details if you are interested. Maybe you can first stick to the main ideas, and I'm going to repeat again and again the important ideas. So we consider a game with n players indexed between 1 and n. We have an action space, which I will assume finite for simplicity for now. So maybe there are some number of actions. Each player takes an action, AI, before seeing the actions of the other players. So you don't know the actions of the other players. You choose an action. Everyone does that somehow simultaneously, and you obtain an action profile, A underline. Now, based on that, each player pays a cost, which is given by a function, fi, which is a function of the actions of everyone. Maybe it depends particularly on the action of player I, but it could depend on the actions of everyone because you have interactions with other people. And your goal as player I is to minimize your cost by choosing your action. So you have to anticipate what the other players are going to play somehow. And the question is, well, is there a somehow stable configuration, choice of actions, such that all the players are somehow satisfied in the sense they don't want to change their action by themselves? So remember, the players cannot coordinate, they cannot cooperate. It's just individual optimization, but your cost depends on other people's choice. So this question is answered by the definition of a Nash equilibrium. So here is the definition in this simple static case with n players. A strategy profile, or rather just an action profile here with a hat. So I will use hat for Nash equilibrium, usually. It is a Nash equilibrium if and only if for every I, player I has no incentive to deviate. Meaning, if you look at your cost based on this action profile and your cost for another action, you change just yourself, not the other ones, then you are worse off. So you are worse off because the cost increases. In other words, A hat I is the best action you can play given what the other players are doing. Convenient notation, I will sometimes use this superscript minus I, negative I, which means the actions of everyone except player I. So in that way, I can rewrite in a more compact way the inequality above by just saying AI, comma, A hat minus I. Example. I will give a few examples, and later on, I will also give a few exercises that you can try to complete. So let's take this example. Here you see that the goal of player I is to be close to a target, one of the actions. So let's imagine that the action set is just 1, 2, etc. until D, so, or it is embedded in the real line, let's say, and you want to be close to some target action. here there is absolutely no interactions between the players. You see your cost depends only on your action. So what is a Nash equilibrium? Well, here you just choose a hat I equals a target, which is the target action. And that's it. You have minimized your cost because you get 0. So very simple case. It is a Nash equilibrium where there is no interaction. All right. Next example, interaction through the mean. So here I want to stress that in mean field games, the interactions are not going to be only through the mean. It can be through the whole distribution, but here this is a simple example with interactions through the mean action. So now your goal as player I is to be close to the mean of other players. Of course, you don't know other players' actions before choosing your own. So if you ask what is a Nash equilibrium, I don't know if there are any suggestions. The idea is you want to be close to the mean, but you realize that any action could be the mean if everyone plays this action. And if one action is the mean action, then you also want to play it because it will be your cost. By the way, I think here there should be a minus sign to make it a cost. So in this case, you realize that you can choose a hat 1 until a hat n, which could be a given action, a, and it could be the same one for everyone. And then the mean is also a, and everyone is happy because everyone is located at the mean. You have concentration of mass, but this could be for any action in A. So this is an example where there is totally not uniqueness of the Nash equilibrium. And in fact, we will see similar examples in mean-field games. When you want to be close to the group, typically this will imply non-uniqueness of the Nash equilibrium. Group aversion, here you want to be far away from the group. So in this case, you pay a cost, which is exactly, in fact, the number of players who choose the same action. So you want to minimize the number of players who play the same action as you. But of course, you cannot choose what other players are doing. So the goal is to be far away from what other people are doing. And if you think about it here for the setting I have chosen, you will realize that the solution, in fact, the only solution is to have a uniform distribution over actions. Because if you have a uniform distribution over actions, then no one can find a better action somehow. So in this example, uniform distribution over actions. And here again, I stress that you don't know the actions of other people, so you need to anticipate. But the definition of a Nash equilibrium is just a stable configuration. It's not about how players are going to find it. We assume that people are perfectly rational and they somehow anticipate everything and they are able to compute this Nash equilibrium. But computing it in practice can be tricky. Exercises. So consider the following cost. You want to be close to a target, but you also have some aversion to the group. So you want to be close to the target, but you don't want to choose the same action as everyone. Right? So in the first case, everyone would choose a target if you had only this part. But because of this term, not everyone is going to choose a target. So question, can you find the Nash equilibrium or one Nash equilibrium or all Nash equilibria? There are multiple Nash equilibria in this case. An example without a Nash equilibrium. So this is a famous example, rock, paper, scissors. So in this case, you have 3 actions. And basically, you have 2 players and one action dominates another action and is dominated by the third action. And if you see that, you realize that there is no Nash equilibrium, at least in the sense I have defined so far, which are in fact pure Nash equilibria. But Nash said every game has an equilibrium point, more or less. Of course, there are some assumptions. And one of the assumptions is that the strategies are allowed to be randomized, or the actions here are allowed to be randomized, meaning you can use randomized choices of actions. So again, you don't know what the other players are going to do. You try to anticipate, and you know that they are rational just like you. So you can kind of guess what they're going to do. and you find your action, but it can be a randomized choice. So what is the mathematical formalism? We still have n players. Each player chooses a mixed strategy. So what do I mean by mixed strategy here? It is an element of P of A. So what is P of A? I will use this notation many times. It means the probability measures on A. Here, A is finite for simplicity. So P of A is just a histogram, or you can identify it with a histogram if you want, or a probability mass function. So a player chooses pi I, but then from this pi I, you sample an action and you get a cost, because everyone is going to sample their own action. And then you get a cost, and what you want to minimize is the expected cost. So it is expected over the choices of actions that are sampled from pi j. So your goal is to choose pi I such that based on your anticipation of what other people are going to do, so all the pi j for all the other players, then your pi I minimizes your cost in expectation. Maybe sometimes you will pick a bad action, but in expectation, you want to minimize this cost. One remark that will be useful later on is that actually you see that fi here depends on the vector of actions. One example could be fi of ai and the average action. So if you remember, the average action was just this average here, average of aj. And this average is random because the actions are random. However, you can imagine that if you take more and more players, if n goes to infinity, we could expect to have a kind of law of large numbers, and somehow you would play against a deterministic action, which would be the average action over an infinite number of samples. So this will be the motivation to pass to the limit, actually. So here is a definition of a mixed Nash equilibrium. It is a vector or a profile of mixed policies, so PA to the power n, such that if I play pi hat I here, and the other players play their pi hat minus I, so all the other policies for the other players, then when I deviate, when I try to pick another policy, my cost increases, right? So the cost increases if you deviate, or at least it does not decrease. It's not possible to decrease it. I will leave it as an exercise to revisit the previous examples for the ones that worked well. And for example, the one with uniform distribution, you realize that you have a simple equilibrium, which is just I choose one action, maybe uniformly at random. Actually, if everyone does that, maybe it's not exactly a Nash equilibrium, or maybe it is, so you have to do the computations because the actions are random. So you can do the computation in this case, checking with this uniform policy and see if it is a Nash equilibrium. In the rock, paper, scissors, it is a Nash equilibrium. So pi hat, choosing 1/3, 1/3, 1/3. So you have probability 1/3 to play rock, 1/3 to play paper, and 1/3 to play scissors. Then this is really a Nash equilibrium. And remember, in that example, we did not have a pure Nash equilibrium. So sometimes randomizing is useful. And in fact, this is true also in some mean field games. So this is not studied a lot in mean field games, at least in the continuous setting. We usually work with pure controls, but sometimes it may be useful to randomize. So now the question, what if n becomes very, very large? In that case, what we expect is that each player has a negligible impact on the rest of the population. So when you go to the supermarket and you buy a product, in practice, you are shifting the price, but not really, because your impact is really, really, really small. So you don't see it. But if you were perfectly rational, maybe you would anticipate that you are shifting the price in the supermarket because the number of players is finite. Population distribution of actions become deterministic, so I will come back to this. And these two aspects should simplify the analysis intuitively. So that's the idea behind mean field games. But to do that, we need to make some assumptions, in particular homogeneity and anonymity. So we will consider models that are more specific than what I've presented before. somehow the examples I gave before were related to these assumptions, but you could consider much more general games. So not all games fit in this framework. All right, so there is a set of assumptions that you need to satisfy in order to have a proper mean field game somehow in the limit. And well, these were introduced by Ladry and Lyons and Keynes, Wang, and Malamé around 2006. So this was a very short introduction to finite population game, just to prepare the background for mean field games. So I'm going to assume homogeneity and anonymity. So there are different ways to name these assumptions. But here what I mean mathematically is that fi is actually going to be a function of ai and the empirical distribution. This does not have to be the case for such functions. Fi could be a different function for all the players, and it could depend on this vector of actions in a very complicated way, which is not related to the empirical distribution, maybe. So this is a kind of strong assumption, but I hope to convince you that you can cover a wide range of models under these assumptions. Here, this delta is a symbol I will use again and again. You can, since the action set is finite, you can think of it as just one if aj is equal to ai, because I'm just using the counting measure if I'm on a finite set. But later on, I'm going to use the same symbol, and it will denote a Dirac mass. This is based on measure theory, and the idea is that you consider a measure which is at one point, which is aj, and then you average these measures and you obtain a new measure, which is called the empirical measure of the population, and which basically counts the players in your space. Formally, when we pass to the limit, we have infinitely many players, but it's not convenient to work with infinitely many players. That's what we do typically in non-atomic anonymous games. But here, in fact, I would like to argue that it's enough to have one representative player, because they are all somehow identical in the sense they all have the same cost function. So if they all have the same function f as a cost, then if they are all rational in the same way, probably they are going to all make the same type of decisions. So I want to study one representative player which chooses one policy pi. From this policy pi, he samples an action A, and the empirical distribution converges to a population distribution. Imagine, so this is this. You can view it as an element of P of A. And when you pass to the limit, hopefully you get another element of P of A in the limit, and I will denote it here by pi prime. And so the cost that the representative player pays is f of A and pi prime. So this is really the same function. You see, f here was a function from A times P of A to R, and I'm using the same function, just passing to the limit inside. Now I need to average over the action in order to get the expected cost. So I have a total cost, which is a function of pi, my policy, and pi prime, which is a distribution over actions of the population. If I know the distribution over actions of the population, then I can choose pi easily. But of course, I don't know pi prime, so I will have to anticipate it. So one representative player, if this player deviates, it has no influence on the rest of the population. And again, I stress that mean field interactions is more general than interactions through the mean. So let me just clarify this. Here, this term is not the same as just taking 1 over n, sum for j equals 1 to n of aj. This would be really the mean action, the average action. But what we have here is really the empirical distribution. So in general, we are going to work with distributions and not just averages of actions or states later on. So the definition of our first type of mean-field games. So pi hat, a single policy, is a mean-field Nash equilibrium if it is optimal against what the population is doing. And what the population is doing is also pi hat, because everyone is rational in the same way. So we can formulate this as a fixed point by saying that pi hat is a minimizer. So I will call this a best response. And it is a best response against pi hat itself. So this is really a fixed point in which you have pi hat, you compute the best reaction, and it gives you back pi hat. So this is to say that if everyone plays this strategy pi hat, I said policy earlier, I will try to keep the term policy for the dynamic setting, but here I will talk about strategy because it's just one step, one shot game. So if everyone plays the strategy pi hat, then my best strategy is also pi hat. So this, in fact, gives an idea for a first numerical method. If you want to compute a Nash equilibrium, maybe you can just iterate. So at each iteration, you apply this best response map, meaning you compute your optimal strategy. So you start with an initial guess of what the population is doing, you find your best reaction, and then you repeat like this. You iteratively compute the best reaction, and maybe it will converge to a fixed point here. So this is a simple strategy. I will illustrate it a bit later. It's simple to implement, but in many cases, it fails to converge. So more details later. In particular, this afternoon, I will show an example where this fails to converge, even in the dynamic setting. I will leave this as an exercise. You can revisit the attraction to the group and the aversion from the group from the mean field point of view. In fact, I will do similar examples in the dynamic case, so I don't want to spend much more time on the static case here. Now, I mentioned that the key motivation for mean field games is to have an approximate Nash equilibrium for finite population game. You remember this was my arrow on one of the first slides going up. So from the mean field game solution back to the n-player game. And I'm claiming that you get an approximate Nash equilibrium. And this is a very strong motivation for mean field games. Otherwise, we could say, well, mean field games is a beautiful mathematical framework, but no connection to practical problems. Another motivation is that usually it will give you a decentralized Nash equilibrium. So in principle, when a player chooses an action, particularly in the dynamic setting, maybe he observes the states of all the other players. This is not relevant in the static case, but in fact, the mean field game equilibrium will usually be decentralized. Not always. For example, when you put a common noise or some more complex types of mean field games, it's not true anymore, but at least for plain mean field games, it's true that usually you will get a decentralized equilibrium, which is also maybe more realistic in practice or easier to implement. So what is an approximate Nash equilibrium? It's the same thing as a Nash equilibrium, except that you add an epsilon here. So what does this epsilon mean? If we think about it for a few seconds, it means that when I play pi hat I, this is my smallest cost possible for any pi I. So I can try other pi i's. I will not get a smaller cost up to some epsilon. So maybe I can be better off by epsilon, but not more than epsilon. If you want, you can pass the epsilon to the other side. Maybe it is clearer, but you can think about this definition a little bit. And this is really the interpretation. So now what is the informal statement of a mean field game equilibrium plugged in an n-player game? Well, if you take a mean field game equilibrium, which is a single policy, just one pi hat. So this is not a strategy profile. It's just one element of P of A, and you plug it in an n-player game, then you get an epsilon Nash equilibrium. So epsilon Nash equilibrium, what does it mean? So if we go back to the definition, it means that if all the players play pi hat, so if all the players have computed the same mean field equilibrium, and if they all use pi hat, then each player taken individually can try to deviate and can try to be better off, and maybe they can be a little bit better off, but at most by epsilon. Now, of course, saying that the mean field game gives an approximate Nash equilibrium is a trivial statement if I don't say anything about the quality of the approximation, because maybe epsilon here is equal to infinity, or maybe it's extremely large, and then the statement is kind of empty. But in fact, the statement is a bit more precise. It says that the epsilon is actually a function of n, and it goes to 0 when n goes to infinity. So in other words, if I take a mean field Nash equilibrium, I plug it in a mean field game, I plug it in an n-player game, I get a good approximate Nash equilibrium, provided the number of players is large enough. Of course, the next question is, what is epsilon n? And in some cases, you can find a bound, and you can have rates of convergence. Notice that this is not the rate of convergence of an n-player Nash equilibrium to the mean field Nash equilibrium. This is more the opposite direction. Starting from a mean field game, you plug the solution in a finite player game. I hope this definition makes sense. Maybe, I don't know if there is any question at this point. It might be good to clarify, because I have introduced a little bit the motivations. First, n-player game, then mean field game, and then one of the strongest motivations for mean field games. So we have kind of a partial picture of the story. And later on, I will move on to the dynamic setting. No questions? All right, so maybe I will provide briefly one illustration of this theorem, just so that you can see the main ideas. So I will not provide many proofs in these lectures. It will be mathematical, but it will not be extremely rigorous. I prefer to give an overview of many things rather than focusing on one direction and specializing very rigorously in one direction. But here is a proof in one case of the previous property. So consider a mean field game with interaction through the mean to simplify. So here, mu is an element of P of A. I can use also the notation pi, but in mean field games, very often we use mu or nu. But in fact, F depends on nu only through the mean. So the mean is the first moment of the distribution. This is not the most general mean field type interactions. This is a special case, but it's very convenient to illustrate the ideas. So the mean is just this expectation here, where you sample A prime and you take the expectation of A prime. I will take phi Lipschitz with some Lipschitz constant in nu and uniformly in A. In fact, it doesn't matter if A is finite, if the set of actions is finite. So maybe, which is what I'm assuming for now. So I'm going to remove the assumption. You just take phi Lipschitz in nu. Let's start with a mean field Nash equilibrium, pi hat. So this is the definition of a mean field Nash equilibrium. If everyone plays pi hat, then my best strategy is pi hat. In fact, I say my best strategy, but what I mean is one of my best strategies, because there might be multiple optimizers. I will come back to this later. The goal here is to show that you get an epsilon Nash equilibrium. So what does it mean? It means that there is some epsilon. In fact, I will do the computation, such that if everyone plays pi hat, so what I mean by pi hat minus I is you take n minus 1 copies of pi hat. So everyone really uses the same strategy, but they're going to sample their actions independently. But the strategy, the distribution of our actions is the same. And then I want to say that, well, my best choice is also to play pi hat up to some epsilon. So how do I see that? The idea is to compare these two terms. And I want to bound these two terms, but I don't know how to do that directly. So what I'm going to do is I am going to plug in somewhere the mean field term. So I know that this minus this, whoops, sorry, without hat, is smaller than 0. I'm just rewriting the inequality for the mean field Nash equilibrium. All right. So I'm going to use triangle inequality somehow, or just decomposition or rewriting of the above expression, introducing this mean field Nash equilibrium inequality. And then I am going to compare these two terms and these two terms. In fact, I will focus on the first one. So what happens here? You see that intuitively they both mean the same thing. They mean I play pi hat and the rest of the population plays pi hat as well. But one of them is for the n player case and the other one for the mean field case. So there should be a difference between them, which is related to the fact that I have a finite population versus infinite population. But this difference is hopefully small. So I'm going to try to bound this term by some kind of epsilon, which depends on n, because if n is very small, maybe the difference is big, but if n is very large, probably the difference is not that large. So that's the idea, but I want to make things precise. So here I'm just doing exactly what I said before, and I'm going to focus on this term I, the first one. So by definition, ji with pi hat and pi hat minus I means that I have this cost phi, which depends on the mean, but the mean is the empirical mean because I have a finite population. In the second case, I have phi of the mean action, but the mean is a true expectation because I have an infinite population. So notice that here I have compared with the second case, I have one extra expectation. If you want, here I can put I and I can put I. It doesn't matter because there is no I anymore. It's just a notation. So I have only one player playing. But in the first case, I have the expectation over the other players, and they all sample independently. So now, how can we compare these two? Well, we are going to focus on comparing the terms inside. So we are going to focus on comparing, this, which is really what happens if I take the terms inside the expectations. And I don't know how to compare them directly, or maybe I could, but I want to do something slightly different. I introduce the empirical distribution minus the ith player. So here you see you have the total empirical mean, and here you have the empirical mean minus the ith player. I use the same normalization, 1 over n. You could put 1 over n minus 1 and compensate somewhere else. For simplicity, I keep the same here, 1 over n. And these two should be very close if n is large. So what does it mean? It means that player I has a negligible impact on the distribution, or rather on the empirical mean here. I only look at the mean and not the whole distribution. So I try to isolate the rest of the population, and then I use triangle inequality, and I will see this term 1 over n times ai appearing, and this term of course goes to 0 because the set of actions is finite, or bounded would be enough, and so 1 over n ai is going to go to 0. And then I am left with comparing a bar with pi bar, and comparing a hat minus y and pi bar. Oh, sorry. So the first one I already decomposed. So now I'm just left with a hat bar minus I and pi hat bar. So this is the mean for the rest of the population except player I. So these players I'm not optimizing over, and then the true mean action. And this term, in expectation, so it is the same that you find below here, but there is this expectation that is going to help us, which is the expectation over the rest of the population. And since everyone is sampling actions according to pi hat, then by the law of large numbers, I expect this to go to 0 as n goes to infinity. And the first term goes to 0 because it's the expectation of one action for one player divided by n. So I hope this convinces you that we can show that plugging a mean field game equilibrium in an n-player game gives an approximate Nash equilibrium. And the computation, so here I make everything fit in one slide. Maybe you can take another look later. Of course, if you are familiar with mean field games, this is probably trivial, but otherwise, please take another look later on. And really, the ideas are pretty similar for the dynamic setting. I will not do them again, but you have to take into account the evolution of the state and use more complicated arguments. But the idea is the same. You compare the n-player game to the mean field game and use some triangle inequality, and you manage to bound the improvements that one player can get by deviating. Before moving on to the dynamic setting, I would like to say a few words about the social optimum. So, so far we have focused on the notion of Nash equilibrium, which means all the players are selfish and they try to optimize their own cost, anticipating the behavior of other people. Now, you could imagine that you have, so this is Nash. Nash is for Nash equilibrium is for the non-cooperative games, finite player games or mean field games. And usually, when I say mean field game, I will mean Nash equilibrium. But it's not the only notion that you can study. You could imagine, for example, the other extreme, where the players are completely, let's say, collaborative or cooperative in some sense, and they want to minimize the social cost, meaning the cost for the whole society and for everyone in the population. So in that case, you can define a social cost. So I will use here J superscript SOC. Pi underline is still an element of P of A to the power n, meaning n probability distribution over actions. For each player, I can compute Ji, so this is the same definition as before. But now, instead of optimizing one by one, I take the average, sum over I, and then 1 over n. And the question is, well, can we minimize? So here, the goal is to minimize over pi underline the cost J SOC pi underline. So this is really an optimization problem over the set of strategies of everyone. But if you want, you could interpret that in two different ways. So interpretation, maybe one, you could say that you have cooperative or collaborative players. And another interpretation, you could say that you have a central planner who chooses the best configuration of strategies and then tells everyone, all right, you have to use you have to use this strategy, you have to use this strategy, etc., which could be realistic. For example, if you think about robotics, maybe you have a large number of robots and you are the programmer and you want to find the best strategies for all of them so that they minimize the total consumption of energy or something like this. So in that case, you can really control everyone, or you can say the players collaborate. Of course, saying that everyone is collaborative or saying that everyone is non-cooperative are kind of two extreme situations. In real life, we are probably somewhere in between. But these are somehow ideal scenarios. I mean, ideal in the sense abstract scenarios where there are already a lot of things to say and to understand before maybe moving on to more realistic settings. In the mean field case, what happens? So let's imagine that you let the number of players go to infinity. And because, so here we need to use again the homogeneity. Oops. And anonymity. Oh, sorry, anonymity assumption. And under these two assumptions, you can pass to the limit, and you can show in general that there will be a strategy which is the same for everyone, because all the players are somehow symmetric and identical. They interact in a symmetric way and they're identical. And so you can look for just a single policy that minimizes this mean field cost. So remember, this was the mean field cost, given that as a representative player, I play pi, and the rest of the population has distribution pi, which means they also play pi. So in that case, I don't need to take any average anymore. And somehow the average is already taken into account in the expectation that appears in the definition of J. So I will come back to this in the dynamic setting, but I just want to present the idea in the static case. The key point I want to stress is that this is an optimization problem and not a fixed point problem anymore. So it may be simpler in some sense because we have a lot of tools to solve optimization problems, maybe more than fixed point problems. In general, probably a fixed point problem is considered more difficult, also from the numerical point of view. So when trying to compute a social optimum, typically we can use all the toolbox from optimization or optimal control, whereas for mean field games, for fixed point problems, maybe it's a bit more challenging. So in general, the two notions are different. I will show some examples later on, and this can be formalized or studied through the lens of the so-called price of anarchy, which has been introduced for some class of games, but then it has been extended to mean field games, in particular in a paper by René Carmona and Christy Graves and Dongjun Tan that I will mention later in the linear quadratic setting. So you can extend this notion to the mean field setting. Basically, the intuition is that you take the best or the worst, depending on whether you minimize, maximize, and how you define the equilibrium, but you take the Nash equilibrium divided by the social optimum, and you look at the ratio. If the ratio is 1, it means you have no price of anarchy. And if the ratio is larger, it means that you have a price of anarchy. So let me just write it here, even though we are going to revisit that later on. So here I would take, for example, the cost in MFG divided, or I will write just the cost in Nash divided by the cost in social optimum. Here it's Nash equilibrium. And I look at the ratio. In general, this one is greater than the social optimum, because in a Nash equilibrium, you optimize individually, and then you look at your cost. But you cannot change the behavior of other people. Whereas in a social optimum problem, the goal is to optimize altogether precisely the total cost. So it makes sense that you get a smaller average cost if you agree with everyone. So in general, the numerator is larger, and if the ratio is equal to 1, it means that you get exactly the same cost in both scenarios. If the price of anarchy is strictly greater than 1, then it means that the Nash equilibrium is less efficient than the social optimum, in the sense that a typical player will pay a higher price than in a social optimum, at least on average. Maybe not for each situation, but on average. In some cases, the two notions coincide. So there is a popular class of games and also mean field games. So here I will present it in the mean field setting directly, such that the two notions coincide. And again, this is true also in the dynamic case. But here it's really simple. In the static case, there is a class of mean field games that we call potential, in which the cost, so which is the function f of a and nu, and remember that nu is an element of p of a, but let's imagine that a is just action 1, 2 until action d, then this p of a is embedded in rd. So I can really view nu as a vector in rd. It has some properties, so the coefficients are non-negative and the sum is equal to 1, but it's a d-dimensional vector. Let's imagine that this function f, or let's assume that this function little f comes from a function capital F by taking the gradient. So let's take the gradient of a function capital F. So here f is a function from, let's say, rd to r. So I can take its gradient and it will be an element of rd. The gradient evaluated at nu will be an element of rd. And what does it mean that I evaluate at A? It means that I take, for example, gradient f of nu. And if I want to take the action I, or let me use another letter. So let me use A, but A is an element of 1 to D here. So this means I just take the D's component. I write a little d here, meaning the a's component. So a is an integer. I take the gradient. The gradient is a vector in dimension d. And then I look at the coordinate number a. And this is my definition of little f. So it looks a little bit complicated, but actually it appears in many situations. You can interpret the cost as the gradient of another function. In that case, let's see what happens. I take the mean field cost, which is a function of pi and nu. So nu plays the role of another pi prime, if you like. In expectation, this is little f, and then I express this expectation. So it is an expectation over a, which is just a sum over a. I choose my action according to P of A, and I get this cost by definition of little f. In other words, I'm just taking the dot product of pi and gradient f evaluated at nu. In this situation, if we make an extra assumption, so potential is not enough. Very often we use the term potential mean field games when we mean potential and a convex f, but I want to stress that here potential is one assumption, and we also need to assume capital F convex. Then if we do that, let's look at the definition of pi hat Nash equilibrium. Pi hat Nash equilibrium means that when I deviate, I will be worse off. So the first inequality is just by definition of a Nash equilibrium, a mean field Nash equilibrium. Second one, I use the relation star that I have described before, rewriting the cost in terms of the gradient of f. And then I say, well, this should be true for every pi by definition of a Nash equilibrium. So in particular, this means that the gradient of f at pi hat should be 0. But because we assume that f is convex, then pi hat should be a minimizer of f. In fact, and then we find that it is a social optimum. Maybe it's not unique if we don't have strict convexity. But still, this property is true. So we have shown the equivalence between pi hat is a Nash equilibrium and pi hat is a social optimum. One example of capital F, I say that this assumption is pretty common. So you can check, for example, if capital F is the so-called entropy, which is the sum of nu A log nu A. then you can check what is the little f that you get, the lowercase f that you get in this case. But I will show some examples later in which you have you use the entropy. And in this case, if you think about it, then the goal will be to do what? So let's imagine that your cost is given by the entropy, in fact, because it will be given by this function capital F. So here the goal is to spread as much as possible. Why? Because you are going to pay a cost, which depends on the density of people at the same location as you or the same action as you, and you want to minimize that. So you don't want to be in a very crowded region. And then the goal is to spread as much as possible, or at least this will be the consequence of the Nash equilibrium. And in the social optimum, this is really the goal of the central planner, is to make sure that everyone has a low density of people at the same location, or low density of robots at the same location. I will come back to these potential games. In fact, we can talk also about variational mean-field games. And this is a class of mean-field games that has been studied a lot, and it inspires numerical methods. When you see the connection between mean-field games and variational problems, minimization problems, then you can use techniques from optimization to solve mean-field games. So before I said, well, fixed point problem is more difficult than optimization problem, maybe intuitively at least. But there are some cases in which your fixed point problem can be written as an optimization problem. And then you can use techniques from optimization. A few exercises to conclude on this. So designing a static mean-field games with exactly 2 pure Nash equilibria, and think about how many mixed Nash equilibria you have. Designing a static mean-field games with exactly 2 mixed social optima. And the last one, static mean-field games with a unique mixed Nash equilibrium, a unique social optimum, but so that their values are different. So maybe not the examples I've presented just before, but an example where you have uniqueness for both, but basically the price of anarchy is not 1. And then the same question, but so that their values are the same. So as you can see, these exercises are more to stimulate your creativity. These lectures are for doctoral students or researchers. So I assume that you are interested in research, and I will mostly focus on creative exercises rather than maybe technical ones in these lectures. But if you are interested in technical aspects, feel free to reach out later on. So as far as I know, static mean-field games haven't been studied too much. There are some cases, for example, some extensions of rock, paper, scissors. In particular, Paul Mueller has worked on this. And also in a survey with colleagues, we have looked a little bit at this setting. At least we have defined it. I think one reason maybe that it hasn't been studied so much is that, in fact, a static mean-field game can be recast as a dynamic mean-field game with a single time step and a single state. So once you see it in this way, I'm going to present dynamic mean-field games next, but once you see it in this way, you could say, well, okay, so everything I do for dynamic mean-field games can be applied in particular to static mean-field games. So maybe there is no point in spending too much time on static mean-field games, except at least for pedagogical purposes. I think many ideas can be explained more clearly. And maybe also there are some interesting features to find. For example, if you think about reinforcement learning, banded problems, multi-unbounded problems are somehow static problems, but they are very important in reinforcement learning. And then you also have Markov decision processes, which are time-dependent problems. Same thing in game theory. If you think about normal form games are very important. So maybe there are interesting properties to study in static mean-field games in case you are interested. All right, so we are done with the static setting. There are several things I explained in the static setting, and I will not explain them again in the dynamic case, but the ideas will be the same. So I hope you can keep these ideas in mind. And now I would like to move on to the case where players have a state that can evolve in time. And they influence this state by choosing an action. So I will continue a little bit, and maybe after 20 minutes or 15 minutes, something like this, we can take a short break and then resume to finish the slides. All right, so I will start, sorry, with finite population games again, but very briefly, just so that you have the motivation in mind. Then I will move to mean-field games. And I will do these first two sections in a discrete time, discrete space setting. In fact, finite number of time steps and finite number of states before moving to the continuous setting. So if you are expert in PDEs or stochastic differential equations, we can jump directly to the continuous case. But in case you are not, maybe it's good to do the finite state, finite time case. And this will be useful also when I discuss reinforcement learning in the last lecture. So I want to prepare a little bit the background. Okay, so here is a summary of the continuous case. You have time, you have space. In fact, we could distinguish between state and action space. And each of them can be discrete or continuous. And in fact, by discrete, I mostly mean finite, at least in these lectures. So maybe we can complete this table at the end of the lecture. The question is basically, so there are several things we need to define. So what is the state of one player? I will denote this by this. So this is a state of a player. We are going to need the mean field. So this will be the mean field term. Mean field term, which I will denote it by n, which can be interpreted as a population state, if you want, or population configuration. It's not really the state of the population because I don't describe the agents one by one. So it's really just the distribution over states, meaning that I don't distinguish between indices or labels of agent. I just look at the occupancy measure, if you want. And I will use m instead of pi because pi will be for the policy or the actions, and m will be mostly for the distribution over states, in fact, because now we have to distinguish between states and actions. And so the question will be, well, how does x evolve and how does m evolve in each case? And in each of the four cases, you have a different way to describe the evolutions of x and m. For simplicity, here I start with the discrete and discrete case. So I start with this top left corner where everything is discrete and in fact finite. Finite population games. So we have a finite time horizon. So here finite means it's not infinite, but we also have a discrete set of time steps. State space is finite. Action space is finite. So we need to distinguish between x and a, state and actions. A player's state will be denoted by x. I will use a superscript I to say it's for player I and subscript t to say it's for time t. The population state, what I will call state, but it's really the mean field term in the n-player game is given by the empirical distribution. So here, remember what I said before about this symbol, delta. This is not just the average position. It is really the average of the Dirac masses or indicator function at the position. So it should be an element of P of X and not an element of X. So maybe I can write this. I don't know if what I'm saying is obvious or not. So let me just spell it out. This is an element of well, actually, it's not necessarily an element of X. It's not even clear that this makes sense, but it could be an element of X, or it could be an element of the real line if X is embedded in the real line. But there are some cases in which X is not even embedded in the real line. Maybe X is just a set of states that are connected to each other. So you can jump from one state to another state, but it's not clear that you can. Maybe there is not a clear ordering, and so the mean of X is not maybe it's not a clearly defined object, but the empirical distribution is always clearly defined. And I'm going to use the terms control or policy. I will mostly use the term control when I mean a deterministic control, meaning that each player takes one action, specific action, and I will use the term policy when I mean a mixed control or a randomized choice of actions. So pi I will be a distribution over actions here, and then you can sample from pi I. You can sample an action from pi I. In these lectures, I'm mostly going to consider the Markovian case. Not always, but most often you can have in mind the Markovian case, meaning that player I chooses her action based on the current time step and her current state. So alpha I evaluated at t and xit, or pi I evaluated at t and xit. There are other possible choices, for example, open loop controls. All right, that's basically the setting for the n player game. But here I have just defined notations. Now I have to say something about the transitions and then about the cost. So I'm going to assume again homogeneity and anonymity. I hope now you are convinced that there are interesting examples, and also it is necessary in order to pass to the mean field limit. So I'm going to assume that the players have the same transition rules. So you see that here's a function p, or this function f here will be the same, and later on, same thing for the cost function. And also, p is a function of the empirical distribution and not of the whole vector of states for everyone. So what do we see here? We see that xit plus 1 is distributed according to some p of xit, ait, and mn. So this means that we have a transition kernel. You can think of it as a Markov chain, where the transitions are determined by the current state, the action chosen by the player, and the empirical distribution of everyone in the population. You could also include the distribution of actions, but I will mostly stick to the distribution of states. And here you could have, sorry, so here there should be n as well. One example is when xit plus 1 is given as a function, deterministic function, plus a random perturbation. So you could imagine that, let me sketch something like this. So at time t, you are in your state space x. So you are somewhere, for example, here, this is your state, xit. Let's imagine you take an action to go there. So this state would be equal to f of xit, ait, and mnt. But then there is an extra perturbation, which maybe makes you jump one state before or one state later. This is the role of the epsilon it plus 1. Of course, it could be much more complicated than that, but this is just an illustration, a picture you can have in mind. So you evolve by choosing your action that makes you jump to a specific state, but then you have some random perturbation. And P would be the distribution induced by that. So Mn is population dynamics, and here, sorry, it should be T plus 1. And somehow there is no convenient way to describe the evolution of Mn. I can just say that this is the empirical distribution at the next time step, and that's it. But it's not really, there is not a very clear function that takes me from, so the question is, how do you go from Mnt to Mnt plus 1 while I just follow the n players? And Mn is random at every state, but as we said before, it's less and less random when the number of players increases. What is the cost function? So here are the notations I'm going to use throughout the whole lectures, basically all the lectures. The running cost, F, is a function of the state of player I, the action taken by this player, and the distribution of the population. So you see that your cost can be influenced by 3 components, instead of just 2, if you are familiar with Markov decision processes, for example, usually you have the first 2 components for a single player, but here you have interaction through this mean field term. And same thing for the terminal cost, xit and mnt, you don't have the action because whatever action you take as a terminal time, it doesn't matter for the rest of the time horizon because the game ends after time t. So somehow the last action does not matter. So we don't put any cost for that. Notice that here, ji is again a function of pi I and the policies used by the other players. Why? So it does not appear completely clearly, but I need this pi minus I in order to compute the evolution of, let me do it in 2 steps. I need this in order to compute the vector x1t until xnt for every t. And this is going to be useful to compute the empirical distribution. So to compute the empirical distribution, I need the policies of all the players, in fact. The definition of a Nash equilibrium, in fact, is just a copy-paste of the previous one. I don't need to change anything. It's exactly the same definition. The only thing that changes is the definition of ji here, which is defined above. But once I define ji, I did all the work, and now the definition of a Nash equilibrium is exactly the same. So I can make basically the same comments that I did before in the static case, but the computation of ji is more complicated, of course. So mean-field games, still in the same setting. So finite number of time steps, finite state space, finite action space. Now we focus on a single state, the state for a single player. So xt without any I. The population state or the mean field state is an element of P of X, and I don't put any superscript n because I don't need that now because we don't have a finite number of players. It is identified with a vector of dimension a number of states as before, except that now it's not a random vector, it's a deterministic vector. So MT is going to evolve in a completely deterministic way, which is much more convenient to analyze. Again, I use the terms control and policy. I focus on the Markovian case. I can make the comments that I could have made earlier as well, which is that the deterministic control is a special case of the mixed policy, if you want, because as a class of all policies, in particular, contains policies of this form, which are focused on one action. So if you give me a control, I can define a policy which has the same effect as this control by just saying when I am in state X, I use with probability 1 the action given by alpha Tx. So this is equal to 1 if and only if alpha Tx is equal to A, and alpha Tx is one specific action for the current time and the current X. But however, if it's possible to restrict to deterministic controls, it's easier, and we are going to do that in the continuous setting. In the discrete setting, I think in general, we need mixed policies, in particular for discrete time and discrete spaces, discrete action spaces. In general, we need to randomize in order to be able to find a Nash equilibrium.
Mathieu, there is one question for you in the chat.
Yes. Thank you. So let me read out the question. Is a mean field term calculable based on the realizations of all agents at each time step, or is it based on their policies? Right. So yes, indeed, I'm going to mention that, something related to that just later on. So thank you for your question. In fact, in the n player case, you really need to have the n player states in order to compute the empirical distribution. If you just know the policies, it's not enough. because you need to have the actual realizations of actions and the actual realizations of states. But in the mean field setting, it's true that if you know the policy, then you can compute exactly the evolution of the mean field. It is deterministic, and so you can deduce the mean field exactly from the policy. And so we are going to reduce to this case, in fact, in the mean field game setting. So this is a very good command. In the n player case, it's not enough to have the policies. We need to have the actual realizations of the trajectories. In the mean field case, it's a function of the policy. Here I have one remark at the end. Maybe that's a question you could have. Actually, I never get this question, and I didn't have it also when I started mean field games. But now I think this should be a very natural question that maybe people have. Why don't we put the mean field? Because here I say, okay, my control is a function of t and xit. Why don't I put m and t here, or mt, right? So in the n player case, it would be a more general class of controls, indeed, and it might give different results. So let me go back here. I could consider alpha of t, xit, and m and t, and this might lead to different Nash equilibria, in fact. But I'm motivated. My presentation of n-player games was motivated by mean field games, and in the mean field game case, actually, so I don't need any I here, this class of controls does not give different Nash equilibria than the one where you just have t and x and xt. So in other words, we don't need, in the mean field game setting, we don't need to put this MT as an input, which is a big advantage because plugging MT would be more complicated. MT can be high dimensional if you have many states, so it would be more complicated for the computations, and it's not needed. I will not go too much into that direction. I will mention it briefly, and maybe I will come back to this in one of the next lectures. But just keep in mind that in the mean field setting, at least in this case, in particular, there is no common noise, etc., etc. So, but in the setting I'm presenting here, you don't need to plug the distribution as an input to the control or to the policy. So it's really enough to have just a function of t and xt. What is the dynamics? Well, they're exactly the same as in the n-player case, except I don't need to put capital N or capital I everywhere. But now the big difference is that for the mean field, we have a perfect description of the evolution of this mean field. If I know that everyone is using the same policy, pi, then I can compute the evolution by multiplying by a matrix, here, a transition matrix, this vector. So remember, MT is a vector. I put a superscript pi to stress the dependence on the policy. If I know that everyone is using the policy pi, I can compute this matrix, this transition matrix, and just do the multiplication in order to compute the evolution, as I would do in a Markov chain to compute the evolution of the distribution of the state. There is one difference that I'm stressing at the end of this slide here, which is that the transition P potentially depends on MT pi. So the transition to go from state x prime to state x, so x is a row, x prime is a column, the transition to go from x prime to x, of course, it depends on x, it depends on the action you are choosing, which is given by the policy. So if I know the policy, I know the probability to choose each action given each state. But it also depends on m pi t. So this is a kind of nonlinear Markov chain, or m pi t has a nonlinear evolution. And so it's more complicated than the standard case, but you can still compute it. In discrete times, there is no issue because you have m pi t, you plug it in order to compute the matrix, and then you multiply by the same m pi t, and you get m pi t plus 1. in continuous time, it will be a bit trickier, but here I hope that it's clear in this case. So I hope this answers the question that we had previously. MT is a deterministic function of pi, in fact. Here there is one thing I'm not giving, which is the initial condition. We should have a fixed initial condition. I will come back to this later on. Definition of the cost is the same as before. If you give me a policy pi for myself and the policy pi prime for the rest of the population, then from this pi prime, I can compute MT pi prime. I don't need to do any simulation of the particle system. I can use the evolution I described before by matrix multiplication, and I find the mean field sequence for all time steps. So I could keep this cost j of pi and pi prime, but actually I will work with a slightly different notation based on the following comments. In fact, as a player, as a representative infinitesimal player, I don't interact really with pi prime. What I interact with here is not really pi prime, it's more the distribution or the sequence of distributions, right? So what I denote m pi prime is what is, if you want, it's an element of, so there are different ways to write it. If you want, you can write it like this. It's an element of p of x to the power t, or if you want, you can write it as a function from t to p of x, meaning for each time step, I have one distribution. So j is really a function of that rather than a function of the policy. So I'm going to use this notation where j is now a function of pi and the sequence of state distributions. Given a sequence of state distributions, I can, so sorry, this should be p of x to the power t. I mix the two notations. So given an m, a sequence of state distributions, I can define the best response map, which is the argmin. So argmin, I already used these notations, but maybe I should have said that this is a set of minimizers. Whoops. Okay. Set of minimizers, and I stress that in general it is a set. It's not, maybe there is no uniqueness. In particular, if you think about it, this is related to some of the exercises I gave earlier. If you have two optimal actions, then you have infinitely many optimal policies, because any distribution on these two actions will be an optimal policy. So you can randomize in many different ways. However, not all these policies are going to give you back the same m. So solving the fixed point problem is strictly more difficult than, in general, is strictly more difficult than solving the optimization problem, because maybe you don't recover exactly the optimizers that you want, and you have to figure out which optimizer is the good one in some sense to solve the fixed point problem. Here is a concrete example. Now, first plot, but I will come back to this in the last lecture, actually, to show you how these were generated. But here I just want to give an example. So the space is a grid word. So X is the state space X is interpreted as a 2D space somehow, but discrete. The dynamics, you move to one of the neighboring cells, so you cannot jump far away. Let's imagine you can just move up, down, right, left, or stay at the same position. For the running cost, you can imagine that you have a cost to move, and maybe you have some discomfort if the region is crowded. So what does this mean? This means that maybe you pay a cost, let's say absolute value of A. So A can be equal to, maybe the norm of A. So A can be equal to +1, maybe +1. Oh, sorry, you cannot do, sorry, in this specific model, if you want to look at this plus, you cannot move in diagonal. So you can do 0, 1, you can do 1, 0, you can do -1, 0, 0, -1, and also 0, 0, 4 possible actions. Cost to move, let's imagine this is just a norm or the norm squared of A, and discomfort if crowded What I mean here is maybe you pay a cost, which is mt of your current xt. So let me stop 1 second. What this means is I take the current mt, which is, I mean, m at the current time, which is the distribution over states. Okay, now we distinguish state and actions. You look at the distribution over states, and you say, I evaluate this at my state, my individual state, and I look at the density at my state. Here, mt is a histogram, if you want, in dimension 2, but it's basically a histogram. So I look at the bin where I am, and I look at the value, and if it is high, then I am not happy. So this means that based on these two ingredients, you can define a function f, which is again a function of x, a function of a, and a function of m. So this function is going to be absolute or norm of a plus m at x, for instance. And you can add constants and you can add other things. This is just an example. You pay a cost to move. If you don't move, you don't pay anything. And you pay a cost if there are many other agents at the same location. If you just do that, you are going to obtain this plot where you see that you have 4 different rooms. This is the initial position. So initially, everyone is in the top left corner. And then they want to minimize their cost. So they don't want to move if it's not necessary. But at the beginning, everyone is concentrated in one state. So if they just stay there, they are going to pay a high cost because of this term. So what they do is they start moving around. People start moving around. And they start diffusing throughout the whole domain, which consists of 4 different rooms. And if you look at the end, this is not very far from being a uniform distribution. The scale is different in each plot, so it's not very far from being a uniform distribution over the 4 connected rooms. So this is a simple mean-field game. In fact, it has a potential structure, so it's related to a social optimum in which the solution is exactly to maximize the entropy, but you can also view it from a mean-field game point of view. If you add a terminal cost, for example, maybe you can try to minimize the distance between x at time capital T and some x target. So you see, before I had an example, my very first example was with a target, but here it's with x target because now we have a state. And so this is the second one is an example of this, where you have a target here. So you start in the top left corner with everyone, and you want to be close to the target at the bottom right corner, but you want to avoid congestion, and you don't want to move because it's costly, but you try to be as close as possible to the target. So I'm not telling you how the solutions were computed yet. This will be one of the goals of these lectures, but this is just to give an illustration and to say that you can already do some sort of interesting examples, even in this basic finite state, finite time setting. All right. So just to provide, let's see, the definition of a Nash equilibrium, or maybe we can take a break now. We are almost at half of the slides, and some of them I can go faster at the end. So maybe we can take a break. I will leave this slide like this. Would it be fine, Francois?
I think this is perfect, Mathieu. Yes, thank you. Okay. When do you want to resume? At which time? 5 minutes is okay, or you want more than 5 minutes?
Sure. For me, it's okay.
So we restart at a quarter to noon.
Yes, that sounds good.
Abdou, do you think this is enough?
If for Mathieu it's okay, I think it's okay for all the audience. It depends on how much time Mathieu would like to take for having some rest. Yeah.
For me it's okay, but I know it was a lot of material. So
okay, so maybe let's say we'll restart at 11:50. Okay, 11:50.
Okay, perfect.
8 minutes.
Okay. Please, everybody, when you log in with your professional name, because if you log in with the smartphone names and brands and so, we cannot identify you. Thank you.
Okay,
Thank
so
you very much.
11:50. Okay, thank you.
Thank
Thank
you.
you.
I'm trying to start my camera, but apparently I cannot. I think I need the authorization maybe to restart my camera.
Let me check, Mathieu, if I can do this from my. No, I can't see anything on my screen that could help you.
Okay.
Maybe Abdu knows more about this.
Yes, Mathieu, please start. Try to do so.
Okay, let me retry. Yes, I think now it works. Thank you very much.
You're welcome.
Okay, before we restart, if there is any question for Mathieu, I forgot to ask this before we stopped. So please don't be shy. You can put any question in the chat. And if there is no question, so we resume.
Yes, okay, sounds good. And indeed, please, everyone, feel free to ask questions. I can address them now, or maybe I will try to save some time at the end for questions, specifically for questions or comments. So feel free to prepare your questions and ask them in the chat. All right, so I will restart from this slide where we stopped. What we did so far was introducing the static setting. Then we started the dynamic setting, n-player game, mean-field game, and I gave this example as an illustration. What I wrote on this slide is just for the sake of illustration. If you look at the papers, you will find the exact form for the code, for the dynamics, etc. But I just wanted to provide the main intuitions. All right, so I have not yet defined the mean field Nash equilibrium in the dynamic setting. So here it is, but it's very similar to what we did before, except that now I will say that pi hat is a mean field Nash equilibrium dynamic policy if it is optimal for one representative infinitesimal player, given the population distribution. And here, usually, what I mean is a sequence. And in fact, the m, again, is an element of p of x to the power t, meaning I have, for t time steps, I have a state distribution. And then we say that the population distribution should be generated by pi hat because everyone is rational in the same way. So this is really the fixed point aspect of the problem. So fixed point formulation, if you give me pi hat, I can compute m of pi hat, which is the m generated by this policy using the transition matrix. But then I look for a best response to this. So here, this, in fact, this, which is generally a set, and that's why I use the this symbol here. This is generally a set, and I will use a symbol BR against m of pi hat. So pi hat should be a best response against n of pi hat, and sometimes it would be convenient to write this also as a function, let's say mf of pi hat. So in other words, if you give me pi hat, I can compute m of pi hat. Again, it's in a deterministic way using this function mf, which is basically the evolution of the Markov chain distribution. And then I compute the best response. And what do I get here? Well, I want to get back pi hat. And this is really the fixed point problem. So you see, it's more involved than in the static case because now we have the state distribution in the middle, but it is really the same kind of ideas to have an equilibrium. So this yields the first algorithm, fixed point iterations. You start from a policy or a control, you compute the distribution, and then you compute the best response or the optimal control, and you repeat until hopefully you converge to a fixed point. This works in some cases, but in many cases it fails to converge. And I will illustrate that this afternoon and also later on in the following lectures. This introduction is again about general aspects of meaningful games. So maybe you are wondering, well, does the problem have a solution? Because if not, there is nothing to compute, right? So yes, in many cases, you can show that there is indeed an equilibrium. And typically, the proof is based on two proof techniques. Usually, it's based on a fixed point problem, a fixed point theorem, sorry. And basically, you have two families, one where you assume strict contraction, and the other one where you assume only continuity and compactness, and you can apply a Brouwer or Schroeder fixed point. So the assumptions are different. You can make assumptions on the model so that you have a strict contraction, or maybe so that you have continuity, and then show existence. I will give an exercise on this a little bit later. And the next question is, do you have uniqueness of the solution? So here I have already mentioned that particularly in the in the discrete case, particularly, it's not clear that you have uniqueness of the best response. In general, you have a set of best responses and you have to figure out which one is the right one somehow. But you may still have uniqueness of the Nash equilibrium. So what I mean by that is you have pi hat, you get the mean field sequence, and then you have a set of best responses, but among them, there is pi hat. Then you are fine. You can solve the fixed point problem. But maybe you have several such fixed points. So when do you have uniqueness? Well, there are at least two types of arguments that are mainstream somehow in the mean field game literature. One of them is, in fact, related to the first proof technique for existence. If you use strict contraction and you apply Banach fixed point theorem, so what do I mean by that? I mean that you have pi hat equal to some function of pi hat, where the function is basically best response composed with mean field. So we are looking at this. If this is a strict contraction, then you have not only existence, but uniqueness. And your fixed point algorithm is going to converge very quickly. Otherwise, another proof technique is based on the so-called monotonicity, which is related to the idea that your cost is monotone with respect to M. So a typical setting is the following. Maybe your drift does not depend on M, and maybe your cost function is with a separate dependence in XA and XM. So separate dependence means you split the dependence in A and M. It's not always true, but this is a very common assumption. In mean field games. And next, you make an assumption on V and how V depends on M. And the assumptions called monotonicity here, which is a monotonicity in the sense of L2. Here I'm writing L2 of RD because I'm anticipating the continuous space case. For now, everything is finite, but you can already have in mind the continuous space case. And in that case, the definition of monotonicity is if you take V of M1 minus V of M2 and you multiply by M1 minus M2, this is non-negative. So what does it mean? It means intuitively that your cost increases with M. So this means that V, of course, monotone could be increasing or decreasing, but here, because we want to minimize, the right sign to take is to say that V increases with M. So what does it mean? It means that when the density increases at your position, then your cost increases as well. So in other words, you don't want to be in crowded region, and a typical example is crowd aversion. You don't feel comfortable when there are too many people around you. And the consequence of that is that the solution of the game will be to spread throughout the domain in order to avoid crowded regions. Of course, if in your cost you have other components like this F tilde, which may create some maybe some spatial preferences, you prefer to go to some location rather than some other location, maybe the solution you will get is not a uniform distribution, as we saw in the maze example a bit earlier. But still, the population will spread a little bit, and typically this will help to get uniqueness. Maybe a counter example is when you want to follow the group. So if you let me put this between quotes, but imagine you take my first example, maybe the second example, where you are attracted towards the mean, and you remember in that case we didn't have uniqueness of the Nash. So here you could say the same thing. If everyone wants to be close to the mean position, then somehow any position could be the mean position and everyone would be happy. This is true modulo the fact that we have an initial condition which may influence also the solution. So here is an example. Maybe I will say just a few words and I will skip the details for the sake of time, but we can come back to this later, or if you try and you have questions, just let me know. So I want to illustrate this fixed point procedure on a very simple example, which is dynamic, because now we are in the dynamic game section, but it's almost static because there is only one step. There is only one time step. So there are two states, state 0, state 1. From state 0, you can go to state 0 and state 1. So this represents t is equal to 0, and this represents t is equal to 1. So it is the same state space at two different time steps. And you can transition from 0 to 1 or from 1 to 0. And this is determined by your action. In fact, so your action is you can go to the other state, or you can stay in the same state. Let's imagine that the running cost is 0. So you don't pay any running cost. And the terminal cost is you want to be close to the mean. So the average state. Let's imagine that at time 0, the initial distribution denoted by m0 is 1/2, 1/2. So you have half of the population in state 0, half of the population in state 1, and this is fixed. So in most of what I'm going to say in the next lectures, the initial distribution is usually fixed. So it's part of the data of the problem in the same way that f is fixed and g is fixed, and you cannot change them. Usually m0 is also fixed. In some cases, maybe you want to consider that m0 is not known and you want to solve for various m0s, but for now, m0 is fixed. So now the question is, well, is there a Nash equilibrium, and what is it? So if we take just a few seconds to think about it, as an individual, you start in one of these two states, 0 or 1. You want to be close to the mean position. So at the beginning, you have half of the population here and half of the population here. Of course, if everyone goes to 1, for example, then you will have a mass 1 here, and the mean will be here, and so you want to be there as well. You want to be at 1, at state 1. And if everyone goes to state 0, then you want to stay in state, you want to go to state 0 as well. Right? Now, if everyone, I don't know, it could be, so could it be anything? Could it be, I don't know, could it be a probability p and a probability 1 over p? Is it possible that, given that I have m0 in this way, 1/2, 1/2, can I have m at time 1, which is p, and 1 minus p for some choice of policy? So actually, yes, it's possible to choose the policy, so randomized over actions, so that part of the people in state 0 will stay here, and part of them will go to state 1, part of the people in state 1 will go to state 0, part of them will stay in state 1, so that I get the distribution p and 1 minus p. So in fact, this is possible for some choice of pi. So maybe here I should put M1 superscript pi. This is possible for any p, right? So for every p, I can find a policy pi such that the distribution at time 1 is it. So I can get pretty much anything at time 1. And if I am one player, I don't know what the population is going to do. I need to base my decision on that because I want to be close to the mean position, but I cannot change what other people are going to do. And I don't know it because they are not going to tell me their policy at the beginning of the game or before I choose my action. So my goal as a player is to anticipate what other people are going to do, assuming that they are all rational, right? So that's why I want to solve this fixed point problem. I really want to know which policies are going to choose, and this will determine the state distribution at the next time step. And if I know that, then I know which action I'm going to take. Maybe I will randomize my action, maybe not. So I hope the question is clear for this simple one-time step mean field game with just two states. And so I am probably not going to solve it, but I just want to show the steps. Let's imagine we just want to show existence. We don't even want to compute the solution. For now, before computing, we want to know if there exists a solution, right? Because if there is no solution, nothing to compute. So imagine I want to use kind of Brouwer-Schroeder fixed point theorem based on continuity of this function phi. So the first thing is I want to show convexity and compactness of what? So remember that phi is a function which goes from the set of policies to the set of policies. In fact, to be more precise, it goes from the set of policies to the set of policies, right? So I could have multiple best responses. And I want to show convexity and compactness. Somehow this is going to be fine if we allow, or since we allow randomized policy. Allow mixed policies. So the underlying idea is you take a finite set of actions, then you take the probability set of probability measures on these actions, and you have a convex and a compact set. But in the continuous setting, it's more complicated in general to get compactness in particular. What about the continuity of phi? So you need to basically, so we decompose phi in, I take a policy and then I get a mean field term, which is a sequence of state distributions. This is my function MF. I want to show that this one is continuous. And then you give me a mean field sequence. Maybe I should do like this. Take a mean field sequence. And I go to the set of policies, right? So what I mean by this, maybe I should clarify. We are not going to need that in the continuous setting, but this is a set of policies or subset of policies. And why do I need that? Because my function BR is potentially doesn't give me a unique best response. So here, if I'm thinking in that way, maybe it's not trivial, but because I have to use set valued map, but it turns out that there is a convenient fixed point theorem, which is Kakutani fixed point theorem. And in fact, the proof of Nash theorem can also be given using Kakutani's fixed point theorem. So in general, you need this, but in the continuous case, we are not going to need set valued map. So I will skip this part, but if you're interested, you can try to do this exercise to complete the proof. Maybe another exercise, you can try to find a dynamic mean field game such that there exists a unique Nash equilibrium, but given this Nash equilibrium, so given the mean field sequence M, the best response is not a singleton. So you really have a set of best responses. And one of them, only one of them gives you back the Nash equilibrium. So if you want, the picture I have in mind is you give me a policy, pi. So in case that was not clear, this is a lowercase pi, and the one before is an uppercase pi, which is a set of policies. So you give me a lowercase pi, which is in this big set of all policies. From here, I compute in the set of all mean fields, I find a point M. Here, I find M pi. And then when I go back here. But maybe the set of best responses is larger. It contains many elements. One of them is the fixed point. Some references to conclude on the discrete setting. So I think the original paper was by Diogo Gomez and co-authors. The link with continuous mean-field games that we are going to discuss next. So if you take discrete mean-field games with discrete spaces and discrete time, and you let the number of time steps and the number of states go to infinity, do you converge to a continuous mean-field games? This has been studied in particular in this paper of Said Hadikanu and Francisco Silva, also related to questions of learning and fictitious play. Then this setting is used a lot in reinforcement learning. So I will come back to this in lecture 6, the last one. And in the past few years, there is a lot of activity on this topic, reinforcement learning for mean-field games. It doesn't have to be in discrete space and discrete time, but this is the most common setting. So it's quite convenient to have this in mind. All right, so continuous time and spaces. And here, I must say that a large part of the literature on mean-field games focuses on this setting. So somehow my introduction so far was a bit non-standard, maybe, compared with most of the literature. But I wanted to present the ideas with as little mathematical tools as possible, trying to simplify the presentations. I hope I managed to convey the main ideas. Now we are going to go into a bit more evolved tools, in particular PDEs and SDEs. Again, if it's not your cup of tea, maybe you can focus on some aspects of what I'm presenting. So first of all, why do we care about continuous time and continuous space? Well, it's more natural for many applications. If you think about it, typically we live in continuous time and we move in continuous space, and it's true for many applications. And it's not so trivial to discretize time and space. So if there is one message of numerical analysis, is that it's not trivial to discretize. Whether we are talking about ODEs, PDEs, stochastic differential equations, if your process is extremely simple, then you can discretize in a relatively naive way and get a good approximation. But if your process is quite complicated and has some non-smooth behavior, for example, then discretizing is not trivial. You can come up with a discretization, but maybe it will not be a good approximation, in the sense when you refine the discretization, it does not converge to the continuous problem. So this is actually a big issue, because you might be solving a discrete problem and believing that you are approximately solving the continuous problem, but it's not true. So let me show you just a very simple example, just to give something compelling. Imagine you are in this grid world that I was describing before, like this. And imagine that you can move only up or down. So you can move up, down, left and right. Up, sorry, up, down, left, right. And you want to find the shortest path from here, from the bottom left corner to the top right corner. Well, in fact, in discrete space, you have a lot of paths. Of course, you can do this. You can follow the diagonal, or you can just do this and this, it will have exactly the same cost in terms of moves, right? So when you go to the continuous setting, this bottom line, following the bottom line and then going up, is still optimal. But of course, in the continuous space settings, this is not what you expect. You would expect just a straight line going through the diagonal, right? And this will be the shortest path. So the shortest path in the grid world is not the shortest path anymore in the continuous setting if you don't pay attention to how you define the moves and how you define the cost. Of course, for this problem, you can easily find a way to fix it, but when you take more complicated processes, it's not easy. So looking at continuous problems is really important, and doing proper discretization is also very important. And last motivation, in continuous time and space, we can use calculus, and sometimes it's convenient, for example, to compute explicit solutions or partially explicit solutions. Calculus is very useful, so I will come back to this in the next lecture when I discuss linear quadratic setting. Here are two examples that were studied previously without mean-field games, and then they were revisited using mean-field games. So I want to stress the differences. First one is continuous time, finite number of states. Second one is continuous time and continuous space. So example one, epidemics. So this topic has been studied for a very long time. One popular model is the so-called SIR model. So S is susceptible, you are not infected, but you may become infected. I is you are infected. R is recovered, you recovered from the disease. And then in this model, you cannot get it again. So we assume that the rate of transitions, so this is in continuous time. So we are talking about rates of transition. The rate of transition from susceptible to infected is some coefficient beta times I, which is the number, or rather the proportion of infected people, infected agents. So here, SIR are really what I denote by ST, IT, RT. These are the proportions of agents in each state. And your probability, or rather your rate of infection, depends on the total number of infected people, or the proportion of infected people. And your rate of recovery depends only on yourself somehow. So this model has been studied a lot. Here you can see the evolution is using ODEs, and this is already a mean field dynamics, because this is the dynamics for the proportion of agents in each of the three states. So here X is contains just three elements, and ST, IT, RT, this ST, IT, RT would be what I've denoted before M at time t, which is a three-dimensional vector. So it turns out that this kind of models have been revisited using mean-field games. In particular, I think the first work I'm aware of are by Gabrielle Touré-Michi and co-authors, and Emma Hubert worked on this during her PhD thesis. And recently also several papers, including with one of my collaborators, Gökçe Dayanıklı, who also worked on this during her PhD thesis. The list is not exhaustive, but there are several works, and in the past few years, for some reason, the topic of epidemic management has become very popular. So there are more and more papers on this topic. The idea is, well, the SIR model is very nice, but you see that the rate of transition from S to I is completely determined. So this is a pure dynamical system. You have two parameters, beta and gamma, and once you fix them, the whole evolution of the dynamical system is fixed somehow. Maybe you need to do some numerical simulation, but there is nothing to choose. But maybe as an individual, you can influence this rate, the rate at which you can get infected, because maybe you don't go out, then you don't get infected. Maybe you wear a mask, maybe something like this, and then you have a smaller probability to be infected. So one thing we did with this paper, in this paper with Alexander Orel and René Carmona and Gökçe Dayanıklı, is we said, well, maybe there is a contact factor, alpha, which is your control, which is going to influence the rate. And the rate is also influenced by the average contact factor of infected people. So this introduces an optimization component because now, or a control component, because now you can choose your control alpha in a way to maybe reduce your probability to be infected. There are other models of this type, so it's not the only one, but I'm presenting one of the models that I'm most familiar with. Oops. So what do we see here? We have a product between your control and the average control of other people, because if nobody in the infected agents go out, for example, let's imagine the contact factor is the intensity with which you go out. If nobody goes out among the infected people, then you can go out, no probability to be infected. If you don't go out, then the infected people can go out, you will not get infected. So really what matters is the product. And this creates a kind of mean-field interaction in the transitions, because it depends on the average action, not the state, but the average action of other agents. So I will leave it as an exercise to write the evolution of the mean-field terms. So what I mean by that is write the evolution for, so the equivalent of the ODE for ST, IT, and RT. This is describing the evolution for a single agent, and then you want the evolution for the mean field. Missing ingredient, in order to have a game, we need to define a cost function. So I will not do it now, but you can check some of the references I gave. For example, maybe you have a cost when you are infected because you don't feel comfortable. You have a cost when you have a small contact factor because you don't feel comfortable for not going out, something like this. So you can cook up a cost function, and then you can define the full mean field game and try to solve it. There are other models in discrete space and continuous time. I will not insist too much on this aspect in these lectures, just from time to time. But there are other models that are similar in spirit. Now, I move on to continuous time, continuous space model. This is a classical model from Crooker and Smale to describe flocking. So the idea is agent I has a position and a velocity. For example, both of them in dimension 3. So let's imagine that xt is in R3, so continuous space, and vt is also in R3, continuous space, and continuous time as well. And you see that the velocity is computed in a relatively complicated way, in the sense that what do you try to do? So you compare your velocity with the velocity of other agents, but you divide by the distance. So if you are far from another agent, this term will be the denominator will be large, and so the comparison with his velocity will not be very important. But if you compare your velocity with another agent whose position is very close, then the denominator will be very close to 0, and then this term will have a big influence in the sum. So the idea is really you try to, so the consequence of that is that you usually see an alignment of velocity. And this is what they call flocking. So flocking means that you might have birds at different positions, but roughly speaking, they're all going in the same direction. But if you have some agents that are far away, maybe they can go in a different direction because the denominator is going to kill somehow the influence of agents that are far away. So this has been also revisited in the continuous setting, in particular by a paper by Keynes and Norian and co-authors. And there are also related papers, maybe not directly on flocking, but acceleration control. So what is the idea? The idea is that we are going to replace this term by a control. So we are going to call it AIT, which will be the acceleration, the derivative of the velocity. And this will be the control. So we are going to choose the acceleration, and we are going to put this term in the cost. In other words, we try to recover a model which has the same features as the concurrence-mail model, except that now the dynamics will be controlled, and there is a cost function which is in charge of incentivizing the agent to align their velocity somehow. So you see there is a shift in the paradigm somehow. Instead of having a pure dynamical system where everything is determined, we introduce a controlled dynamical system with a cost function. And when we solve everything, we hope to recover the same effect as the concurrence-mail model, meaning flocking and velocity alignment. So this is a model of Norian et al. In this box in green, and you see that here I'm giving immediately the mean field model. You see that we recover the comparison of velocity divided by comparison of positions, but there is an integral which replaces the sum, and here we have the empirical distribution. Notice that this is really the state. This is not the empirical distribution of state and actions, because the state has two components, x and v.
Mathieu, you have one question in the chat.
Yes, thank you. Thank you very much. Okay, very good point. Thank you. So the question is, what is the typical value of beta? So thanks for asking this. I was going to mention just now. So in fact, there is a parameter beta here, which influences which influences somehow how much you feel the other agent. So if beta is very large, it means what? It means that this denominator is going to go to 0 very quickly. Somehow, if x prime is close, or maybe not 0, but is going to go to epsilon to the power beta. So one choice is beta is equal to 2. Sorry, beta is equal to 2. Beta equals to 2. In that case, what happens is just quadratic growth. Another case, beta is equal to 0. In that case, you completely remove the denominator, right? So if you take beta is equal to 0, the denominator becomes 1, and you just have v prime minus v integrated over the whole population, right? So this means that you are going to try, when beta is equal to 0, the cost creates an incentive to align the velocity with the whole population. So I cannot swap the integral. Yes, actually I can, because there is no absolute value. So here this will be, we are going to get v minus, we are going to get actually v bar minus v squared, right? In this case, if I take beta is equal to 0, I take the integral, I integrate v prime, this gives me v bar, the average velocity, minus v. I just try to be close to the mean velocity. But when you take beta larger and larger, for example, beta is equal to 2, or beta even larger, then you feel only local velocity. Meaning that you try to align your velocity only with neighboring agents, neighbor in terms of position. Now, the question is, what is a typical value for beta? So I don't have a typical choice in mind. If you try, maybe you can try to fit the model with some data, and then you will find some specific value. I suspect there are many normalizing constants everywhere, so I don't have a specific value of beta in mind, but I think it's good to keep in mind the idea is that when beta is smaller, you feel the influence of more and more people. And when beta is larger, you feel the influence of only neighboring agents. All right, so here just a few more plots. So you can do simulations indeed in dimension 3+3, where on the left you see birds going through let's say towers, for example, or buildings. So there is also the link to a video. How did we generate this video? Of course, one way is to just use directly the flocking model of concurrence-mail, but another way is to use the mean field game. You compute pi hat, let's say, which is the equilibrium policy. Then you plug plug it in the n player dynamics, or I should say n birds maybe, in the dynamics with n birds, and then you can do a simulation. So at the end, you recover a dynamical system with n birds, but you started from the mean field game, computing the mean field policy, and then plug it in the system. And then you can do some animations like this one in Unity, which was done by Sarah Perrin. So Sarah Perrin worked a lot on reinforcement learning for mean field games during her PhD thesis. All right, so maybe to justify how we can pass to the limit, I will not insist on that too much. All right, sorry, there is one more question. When we have a game, why? Okay, thank you. So when we have a game, why do we need a cost function? So yes, thank you. So here somehow, if you have just a dynamical system, you don't need any cost function. You just have the dynamics somehow. But now if you introduce a control, so like here, I introduced a control. So now it is a controlled evolution. But how do we choose alpha t? So I could say, I'm going to tune alpha t in different ways, and I'm going to see what I get. Okay, in that case, I'm not really optimizing anything. Maybe I'm just looking at the result and see if it looks realistic, which is not so different from what you can do with just a dynamical system like this one. Maybe you can simulate the dynamical system, tune a little bit the value of beta, tune a little bit the value of epsilon. You have these two parameters. Maybe in some models you have even more parameters. You tune a bit the parameters, you run against the simulation, you see what you get. This would be close to agent-based modeling, or maybe pure dynamical systems. The difference here is that we try to model what the agents have in mind somehow, what they're trying to optimize. So we design a cost function that seems realistic. So there are some cases in which we really don't know. There are some cases in which we know. For example, if you have a mean field control problem in which you want to program your robots, maybe you have a very specific cost, which will be the energies they are going to spend, the tasks they are going to complete, and this kind of thing. So there are some situations in which you have a very specific cost functions. There are some situations in which you need a little bit of imagination, but then you introduce your cost function, and after that, you have really the game, which is, what I mean by game is that the Nash equilibrium, where each agent tries to minimize their own cost. So if there is no cost function, there is nothing to minimize, and then we don't really have a game or a notion of Nash equilibrium. So I hope this answers the question, but I know the connection between dynamical system and this mean field game can be a bit confusing, and why do we design the game, and how we design the game is yet another topic. So I will not go too much into the question of modeling, but from time to time, I will try to give some examples, just taking them from the literature. All right, thank you. So one question is, how can we justify passing to the limit in the continuous case? And this is a different question from taking the mean field solution and plugging it in the n-player game. Here's the question I want to tackle is, how do you pass to the limit rigorously? So this has been studied a lot in physics. And in fact, that's one of the underlying ideas of mean field games, that their mean field come from statistical physics. So I borrowed this illustration from the Wikipedia page on diffusion that you can check. And you see one particle in the first box, many particles in the second box, and the last one is the diffusion model using an ODE or a PDE here. So for a single particle, typically the dynamics will be given by a Brownian motion. W here will be a Brownian motion from the standard Brownian motion. And you can look at the macroscopic evolution of the distribution denoted by M. So I will not go too much into the details. Sometimes I will use M for the measure, sometimes for the density. I will not be too rigorous on that, but roughly speaking, the M, the distribution satisfies a PDE in which you have the time evolution is given by the Laplacian, which is the second order derivative. Here, sometimes this coefficient I will denote it by nu sigma square over 2, just to simplify the notation. So passing to the limit has been studied a lot by Katz, and there is also a monograph by Snitman on propagation of chaos, which justifies passing to the limit. For particles, you can even include a drift in the evolution. So it is this term B that I will call drift, function of t and xt, and this induces an extra transport term in the PDE here, which is the divergence. So you can think of it as a first order derivative of B times M. So this drives the evolution in a certain direction. If you want, B gives the direction and sigma dW gives some noise for the evolution. Okay, what about the mean field game situation? So here we have n players, and the dynamics that I will usually take in the continuous setting, continuous space setting, is this one. So here we have again dW indexed by I, because I assume that each agent has a different source of noise. If you want, it's a little bit the equivalent of the epsilon I when I was doing the discrete time setting, but now it's a Brownian motion. B is the drift influenced by the current state, the action taken by the agent. Here, for simplicity, I take a Markovian control function of t and xi and pure. So this is Markovian and pure, so no policies. I will not justify this too much, but basically in the continuous setting, in most cases, we don't need randomized controls. So I simplify immediately these notations. And we have the empirical distribution here. So you see, I'm immediately imposing the assumptions of homogeneity, because it is the same B for every I, and anonymity, because people interact through the empirical distribution, which is defined here. And now delta is really a Dirac mass. So here again, Mn is stochastic, but as n goes to infinity, we expect Mn to converge to some Mt, which would be a deterministic, which would have a deterministic evolution, and which would not be influenced at all by agent I. So you see here, this, I can write it as 1 over n, sum for j different from I of delta xjt plus 1 over n delta xit. So player I has an influence on Mn, but it's a small influence and it goes to 0 when n goes to infinity. So in the end, we expect to have a deterministic Mt. It's more difficult to justify this in the mean field gain setting because you have a control which influences the optimization. So it's more difficult than just standard propagation of chaos, but there have been many works in this direction. In particular, I would refer to the book of Cardaliaguet, Delarue, Latreille, and Lyons on this topic. And also Dan Reichert has some really excellent lecture notes on his webpage, and also in the monograph for the AMS lecture notes edited by Françoise that I mentioned earlier. So if you want to know more on this topic, I will not give any detail, but this is also an interesting question. So in the mean field setting, jumping directly to the mean field limit, you have one representative player, so I drop I, and you have the evolution of the mean field. So you remember that in the discrete time case, we had mt is equal to some matrix pt, sorry, mt plus 1 is equal to some matrix and pt times mt. This is the equivalent in the continuous case. So it looks like what I've described before for the particle system, except we have this control alpha here. So if I want to stress the dependence on alpha, I will write m superscript alpha and x superscript alpha. So I will write x alpha and m alpha if I want to stress this dependence. What about the cost function? So we have the dynamics of the agent of the mean field. What about the cost function? So running cost will be a function of t, xt, alpha t, and mt. In fact, we usually distinguish two cases in the mean field game literature. Intuitively, there is a case of interaction through the whole distribution. So mt here is really the whole distribution. So it's an element of p of rd, let's say, if x evolves in rd. But in general, we take it regularizing. So a typical example would be I take mt and I take the convolution with some regularizing, let's say, Gaussian kernel, and I evaluate this at xt. So this is, let's say, a Gaussian kernel. What does it mean? It means that you are at some location, xt, and basically you take a small, not really a ball, but you take a Gaussian distribution around you, and then you integrate the density with a weight that depends on this Gaussian. So if there are many people here, maybe you are not going to see them because you take the convolution with a Gaussian around you. The other case is where you have a density and you interact with mt at xt exactly. So only at your location. So this is even more strict. It's exactly at the same position as you. How many people there are at the same location as your location. Of course, you can do other things. You can consider non-smooth dependence on mt, etc., etc. So there are many, technical challenges, but these would be maybe two relatively common cases. So the next step is how can we characterize and compute Nash equilibria? So before computing, now we have the definition. So we can say, let's use the definition. But as I've mentioned before, from the definition, you can use fixed point iterations, but that's about it. And it doesn't always work that well. So what we are going to do is I'm going to introduce optimality conditions, or rather equilibrium conditions, to characterize the Nash equilibrium in a different ways than just the definition. And then we can try to solve these optimization conditions using numerical methods. So, okay, in fact, what I'm going to present here is based on the two types of, let's say, arguments. One is Bellman principle for dynamic programming, and the other one is Pontryagin maximum principle for deterministic or stochastic problems. And well, I cannot do a full course on optimal control. Maybe some of you, most of you, I don't really know, are familiar with this. So I don't know the proportion of people who are familiar with that. So in the next slides, in this section, actually 4, I have summarized the main ideas and the notations I'm going to use. So I will review that briefly. And well, if you are not familiar with optimal controls, and I can provide more references later on, feel free to send me an email. Most of the literature start like this, let's say. So I picked 2 examples from the literatures. First one, you see this paper is devoted to the analysis of second-order mean field games, and this is the mean field game. But it's not really what I described before, right? So this is immediately a PDE system that describes the mean field game solution. And similarly, the next reference is a forward-backward stochastic differential equation system that describes the mean field games. And so what I want to explain briefly here is how do you go from the definition to these? And in the next few lectures, we will try to solve these systems in most cases. In some cases, we will use the definition. In most cases, we will try to solve these systems. So let me start with a discrete setting. We are going to introduce a value function. So what is a value function? It is a function of a state, and it tells you what is the best cost you can get starting from this state. And then maybe you have a distribution over states and you can take the expectation. But the idea is if you start in this state, what is the best value you can get? In mean field games, the value is going to depend on the mean field term. So you see, whether it is for the terminal cost or whether it is for the running cost, I need to know MT. So in fact, this value function depends implicitly on MT. So Nevertheless, I introduce v, which is a function of time and state. At terminal time, it's just, so sorry, this should be little x because it's a function of x, any state, potentially, and the mean field, which is given to me. So here, I assume that mt for t equals 0 to capital T is given. And then we can do backward induction and say that the value at time t will be given by taking the best action in order to minimize my running cost plus the value function for the state I'm going to reach by taking this action. So this is the definition of the value function. In fact, this is the Bellman principle, but you can take it as an equivalent definition. And this gives you a concrete way to compute it, in fact, by doing a so-called backward induction. So at terminal time, there is nothing to compute. It's your terminal cost. That's it. It gives you the value. And then you go backward in time. And at each step, you solve an optimization problem, which is for a single action. So hopefully, this is not too difficult to solve, at least if you have a finite number of actions. How do you recover the optimal control? So remember, the optimal control would be a function of t and x. And in fact, this will be by taking the arc mean over the actions for the actions that give you the minimum here, or one of the actions that give you the minimum. All right, so what do we get? I just described the value function, backward induction, but we also need the evolution of m because it appears in the backward equation. So I need to write what I had already written before, maybe in a slightly different form, but this was the evolution of m. So you remember that mt plus 1 is equal to pt times mt. In fact, this depends on a specific policy, but I'm just spelling out this multiplication here. Now we have a coupling between the forward equation for the evolution, because you see that it depends on pi, which I am going to find by taking the arc mean of the value function, and the evolution of the value function, which is backward in time, in fact. So if you are familiar with optimal control or maybe Markov decision processes, it is just for the backward part, but we have a coupling with the forward equation. And I'm going to repeat that many times because this is really one of the key difficulties in mean-field games. We have this coupling between the forward and the backward equation, and we cannot solve one before the other. In the continuous setting, there are 2 points of view, PDEs or SDEs. So we can still define the value function, function of t and x for a given mean-field flow. We do dynamic programming, and then we couple the dynamic programming equation with the mean field evolution. So in the continuous space, continuous time setting, we usually define the Hamiltonian. And here I define it as a max over A of minus the Lagrangian, where the Lagrangian is the sum of the running cost, here, the running cost, and the drift multiplied by P, which is the adjoint variable. Here, I'm not going to justify anything. Maybe I can provide some references on optimal control. The value function U, so U is the value function, satisfies PDE, which is called the Hamilton-Jacobi-Bellman PDE, or HJB for short, which is a backward equation because it starts from a terminal condition, and then it goes backward in time, and you see it involves time derivative, spatial derivative of second order, and the Hamiltonian. In general, I'm going to give examples later. In general, the Hamiltonian is nonlinear in gradient U, and this is what makes this PDE difficult to solve. Okay, in general, there is uniqueness of the action, provided you have strict convexity assumptions on the Hamiltonian, which we usually make. Just a word of caution. There are other conventions for the definition of the Hamiltonian. I mean, at least one other convention, which is to take the mean over A of the Lagrangian. So it's equivalent, except that the minus sign is outside instead of being inside the optimization. So you would have an extra minus sign in the PDE. Okay, so if you check a paper on Nifl game, or maybe in my, I will try to be consistent throughout the lectures, but if at some point you see a minus H, it's not necessarily a typo. It really depends on the definition of the Hamiltonian. So just be careful. Also, when you implement, trust me, you can make this type of mistakes very often. So be careful with the sign of the Hamiltonian. All right, so we end up with a forward-backward PDE system where you have the forward equation for the mean field and the backward equation for the value function. Yes, actually, most often what we take for B of X, M, X, A, and M, sorry, A, M, is just equal to A. This is a very common setting. And in that case, the PDE system is a bit simpler than in the most general case. I will come back to this PDE system again and again. So this is just a teaser somehow, or just to prepare the background. Maybe you can take a look later. The key point is, again, we cannot solve. So I would like to solve the forward equation. This is what I would like to know, maybe the evolution of the mean field, but I don't know that because I need the value function or the gradient of the value function. So now I look at the value function. It solves this PDE, but this one depends on M. So I go back to the first equation, but then I'm stuck because they depend on each other. So the key point is really, I cannot solve the forward equation for the evolution of the mean field before knowing what control people are going to use. And I don't know what is the optimal control before I know the evolution of the mean field. I cannot solve the single agent optimization problem before solving the mean field. And this will be really the core difficulty to solve mean field games numerically. At least one of the core difficulties. Existence, I have already mentioned that here. I'm thinking about existence for the PDE system, but it's basically the same thing. Then I have three remarks before moving to the stochastic case. In some situations, the mean field game model can be interpreted from a variational point of view. So this is analogous to potential games that I've described before in the static case. And there is something analogous in the continuous time and continuous space setting. I will come back to this in lecture 3. Mean field games with common noise. So in that case, you have an extra Brownian motion that affects everyone in the population. Then if in some sense, the agents are correlated because of this common noise. And what you get in this case is not two system of PD, I mean, a system of two PDEs, but a system of two stochastic PDEs, which is more challenging to study. And one way to study it is through the master equation, which is a PDE, a deterministic PDE, but it is on the space of measures. So this is the price to pay. And here I refer to this monograph of Cardalaguet, Delarue, Lasry, and Lyons on this topic for more details. I will not talk too much about the master equation, a little bit later on, but not too much. Exercises. So in fact, the first one will be useful for this afternoon, but you don't have to do it right now. Maybe you can do it later. Linear quadratic. So this is a special instance, special case of the drift, the running cost, the terminal cost, with interactions only through the mean. So again, mean field game is more general, but here interaction through the mean. Another one, an example with congestion effect. Another one with crowd aversion effect. So here the exercise is take these cost and drift and try to write the PDE system. Try to write the Hamiltonian and try to write the PDE system and see what you get. I think it will help to make things more concrete. Derive optimality conditions for the social optimum problem. I will discuss that this afternoon, but for now I leave it as an exercise. Here is an example where you can show existence and a uniqueness of the PDE system in a special case. This is in a book of Bogachev et al. On Kolmogorov-Fokker point equations. They have one section on Mifflin games, and the proof is really not that long. It uses a fixed point argument, more or less like what I described before. So it can be interesting if you are into PDEs.
Mathieu, there is a question for you.
Ah, yes. Thank you. So the question is now, because XT has a stochastic dynamic, MT is the density of the normal distribution. Okay, so thank you. That's a good question. So the question is actually, let me go back. So the question is, XT has some noise. So I go back. Sorry, I would like to do the continuous setting. Okay, so XT has some noise. And the question is the distribution of XT a Gaussian distribution? Well, actually, no, because of the control. So sorry, actually, I was trying to find, I think it's in the previous section. If I go to this dynamic setting and I go here, you see that here XT is influenced by the control, and as a consequence, the distribution is not going to be Gaussian in general. This, if XT was just the Brownian motion, and if it starts from a Gaussian distribution at time 0, then yes. But because of the initial distribution, because of the drift, and in particular the control, maybe it's not going to have a Gaussian distribution. Okay, so I think now there are a few minutes left. If you have questions, I think it's a good time because I can just do the following slide later. So feel free to ask questions now, and otherwise I just take a few minutes to finish the slides. Okay, thank you. Can we apply min-field games to sports? Why not? I'm not sure which sport. So maybe you need either a sport with a lot of players to do the min-field approximations, or you need to have some min-field aspect somewhere. I think some people have tried to apply min-field games to some kind of competition, so min-field games with a ranking, but in most, maybe marathon or something like this, it could make sense because you have a lot of people running, but otherwise I'm not sure. All right, so if there are no further questions, maybe I just take the last few minutes to finish. Again, feel free to ask questions. Approximation rate. So I was not planning to discuss too much the approximation rate, but I can come back to this later, maybe. I assume you mean the approximation rate from finite player to min-field game, maybe. So I can add a few comments about that later on. Sure, it's a good question.
Okay, Mathieu.
Okay.
Is there any here? Please, Mathieu.
Sorry. Okay. Please. So what I just wanted to say is the next few slides, but I can cover them later. So the idea is the SDE viewpoint. In fact, there are two parts. One part is starting from the Bellman equation. So let me jump directly here. You define yt equals u of t and xt, and then you apply Ito's formula, you use the HJB equation, and you find a backward stochastic differential equation for yt. Another approach is to use Pontryagin stochastic maximum principle. So here, I start really one step back. I start from the ODE, then the SDE without mean field, and then SDE with mean field. And you see that at the end, what you get is a backward stochastic differential equation for yt, but it is of mean field type because it involves the law of xt at equilibrium. So in the end, in general, you get forward-backward system of Makin-Vlasov type. So here I refer to the book of François and René Carmona on this topic for many details on this. Bottom line is you have a forward-backward system. It's still forward and backward. You see the equation forward starts at M0, equation backward has a terminal condition. You have mean field interactions. the law of xt is not necessarily Gaussian, and you want to solve this system. So this will be one of the topics I'm going to discuss later, how to solve this numerically. Exercise, write the forward-backward system for some of the examples to make things more concrete. So, conclusion, I think there are 2 minutes left, maybe. We have discussed n-player games, how to move to a mean-field games using homogeneity, anonymity assumptions, which are basically interactions in a symmetric way, and all the players are identical. Connection in the 2 directions. It's true, I've not seen anything about the rate of convergence. I can mention that later, or add something in these slides, maybe. Several settings, starting from the static one, which was mostly for pedagogical purposes, and then dynamics, discrete or continuous. Maybe you can fill in this table that I've shown at some point for the evolution of X and M in every setting, and optimality conditions, which will be the basis for many of the numerical methods, or rather the aim for many of the numerical methods. To conclude, there are many extensions of what I'm presenting here. For example, ergodic cost. You can include the action distribution instead of state distribution. You can include common noise. You can have several populations. So these assumptions are somehow different settings. And then there are some settings where you try to go beyond the full homogeneity of the population, which is of course important for applications. So several populations, mean field type games, so-called mean field control games that are pretty recent, major player, cycle-based mean field games, graph-on games where you have a graph of interactions, etc., etc. So there are various settings which go beyond what I'm presenting here, but for the sake of simplicity in these lectures, I will focus on, let's say, plain mean field games with a fully homogeneous populations to explain the main ideas. So if you want more references, feel free to take a look or to ask me later on. And thank you very much for your attention. I think I will